Let's do an example, again, slightly more complicated. Example 6. This time we'll let our function f of xy equal xy, and we'll do x squared minus y cubed. And we'll let our curve c of t equal cosine of t and the sine of t. And in case you don't recognize that, this is a parameterization for the unit circle moving in the counterclockwise direction. Okay, and we want to evaluate the integral in the interval 0 to pi over 2. So as t moves from 0 to pi over 2, well, if t moves from 0 to pi over 2, we're going to move along this path right here, and we're going to stop right there. So we're going to integrate this function along this path from here to here. That's what we're doing. Well, let's go ahead and do it. So f of c of t is equal to, well, this is x, this is y, so we put it in there. So we get cosine of t, sine of t. Let me write that a little bit better. Cosine of t and sine of t. And then we have x squared, which is cosine squared of t, minus y cubed, which is minus sine cubed t. Okay, now let's do c prime of t, or I'm going to write it as dc dt. So when I take the derivative of cosine t, I get minus sine t. I take the derivative of sine, which is cosine t. And then I go ahead and I form the dot product. So I take this dotted with this, and I end up with the following. And I'm going to shorten the notation. I'm just going to do f dot dc. I don't want to write out all the c's and t's and things like that. So f dot dc, it's equal to, well, this dotted with that. So we're going to have this times this. So it's going to be minus sine squared. Let's write this slowly because we don't want these random lines to show up. Minus sine squared t cosine of t plus this times that plus the cosine cubed of t minus, okay, actually, you know what? Let me go ahead and erase this. Let me start on the next page. I want this particular integrand to be very, very clear. So f dot d of c is equal to minus sine squared t cosine t plus cosine cubed t minus cosine t sine cubed t. So when you take the dot product of those two, you're going to end up with that. That's your integrand. So the integral of f along the particular path that we chose in the given interval is going to be the integral from 0 to pi over 2 of minus sine squared t cosine of t plus cosine cubed t minus cosine t sine cubed t dt. Excuse me. This is the important part, being able to get here. The rest of it is just basically just technique. Now, I'm not going to go ahead and integrate this manually. What I did when I did this is I just put this into my particular mathematics software. I use Maple myself, and it gave me the answer, nice and quick. And the answer to this is 1/12. There you go. That's a line integral. You're doing the same thing that you did with single variable calculus, except now the line is no longer just the x-axis. We've taken that x-axis, and now we can integrate a function along any curve we want. In this particular case, we've integrated a vector field, which is a function from R2 to R2, or R3 to R3, or R4 to R4, where the dimension of the departure space is the dimension of the arrival space. In the next lesson, I'm going to talk about so what we've done here is we've integrated a function from R2 to R2. We've integrated a vector field around a curve. In the next lesson, we're going to talk about multivariable functions, let's say an R2 to R, where the arrival space is just the real number line, dimension 1, what we've been dealing with, functions of several variables. You can also do line integrals of functions of several variables, not just a vector field. So we'll define that in a subsequent lesson. But for the time being, all you really have to worry about is just this basic definition. Form f of c of t, form c prime of t, take the dot product, you end up with a function of a single variable, t, and then you just integrate it, just like single variable calculus. Okay, thank you very much for joining us here at Educator.com. We'll see you next time. Bye-bye.